This NMR challenge we have taken from Pavia Spectroscopy book 4th edition. Page number is 227, problem is 16. We have to determine the structure of organic compound having molecular formula C5H9 and O4 from the given IR data, normal carbon NMR data, DEPT 135, DEPT 90 and 1H NMR data. By the end of this video, you will understand how to calculate the index of hydrogen deficiency, how to interpret 1H and 13C spectra, how to analyze advanced spectra such as DEPT 90 and DEPT 135, and how to integrate all the data logically to identify the correct structure of the organic compound. So let's solve this problem step by step. So first is we will see IR value. So there are three IR value. One is 1750 centimeter. This IR value indicates the presence of ester group in the molecule, because 1735 also indicates the presence of ester group in the molecule. So this is bit higher. Okay, so maybe there could be a electron withdrawing group which making it higher. And second IR value is 1562 per centimeter. So this, if you remember, this value is belongs to the nitro group, and in your molecule there are nitrogen atom. So this could be belongs to the NO2 group. There is another value 1320 per centimeter, and this value also indicates the presence of nitro group, but this is belongs to different stretching. I think it is belongs to the symmetric stretching, and this one is for asymmetric stretching of the nitro group. Okay, now we will calculate index of hydrogen deficiency. So index of hydrogen deficiency has formula 2C plus 2 plus nitrogen minus hydrogen minus halogen divided by 2. So how many carbons are there? 5 carbons plus 2. How many nitrogens are there? 1 minus hydrogens are 9, halogen 0 divided by 2. So this molecule has 2 degree of unsaturation. So 1 degree of unsaturation you can assign to the ester group, and another degree of unsaturation you can assign to the nitro group, right? Okay, now we are going to interpret carbon NMR. So in the carbon NMR there are 1, 2, 3, 4, 5. There are 5 signals, right? 1, 2, 3, 4, 5. And one signal is 14 ppm. This is 16. This is 63, 83 and 165. Look at this signal 165. This 165 is corresponding to the presence of carbonyl group of the ester, right? Presence of the carbonyl group of the ester, or it could be the amide also, because amide carbonyl group also comes around this. If the molecule has nitro group, then it means the nitrogen is already belongs to the nitro group, so this does not have any amide group. Now look at the 13C DEPT NMR. This 14 ppm is in the positive, so it belongs to the methyl. 16 also belongs to the methyl, it is in the positive phase. 63, it is in the negative phase, so it belongs to the CH2. And look, this CH2 may be attached to the oxygen, or it could be attached to the nitro group. So right now we don't know. Now 83 is showing in the positive. So 83 showing in the positive means this belongs to the methane carbon, and this methane carbon could be attached to the electronegative withdrawing group. That's why it is going to 83 ppm. And 165 of course will not show any signal, because this is belongs to the carbonyl group of the ester, which does not have any hydrogen. Now let's look at the DEPT 90 NMR, which is very important. So this is no signal because it is belongs to the methyl. There is no signal, there is no signal, but 83 is showing the signal. So as we said, this is methane carbon. Okay, and of course, because DEPT 90 does not show signal for the methyl carbon or quaternary carbon or CH2, it only shows the signal for the methane carbon. Okay, from the carbon NMR we have following informations. This compound has ester group, it has methane carbon, it has CH2 which is attached to the electron withdrawing group, electronegative atom, and 2 methyl carbon. Okay, now we are going to interpret 1H NMR. The 1H NMR is showing very nice splitting pattern. How many signals are there? There are 1, 2, 3, 4. 4 signals are there. It means there are 4 types of hydrogen. And signal 1, this is triplet, and it is around 1.3 ppm. Triplet belongs to 3 hydrogen. So how many neighboring hydrogen? N plus 1 rule. So it is 2. It has 2 neighboring hydrogens. It means this compound has ethyl group. If it has ethyl group, then there should be quartet as well from this CH2. And second signal is around 1.7 ppm, and it is doublet, belongs to 3 hydrogen. So this doublet means it has neighboring 1 hydrogen, and this means it is something like CH3 attached to CH. So this methyl is attached to CH. we have already seen in the carbon NMR that compound has one methane carbon, right? One methane carbon, so it could be this one. Now look at the signal third, which is quadrate. Yes, it is around 4.3 ppm, and this quadrate has integration value 2 hydrogens. So this indicates that there is a 3 neighboring hydrogen, and it could be like this: CH2, CH3, right? But the interesting part is that this CH2 is coming in the de-shielded region for 4.3 ppm. So this could be attached to the oxygen. It could be like this. And now the last signal is also quadrate, which is 5.2 ppm, which is quite de-shielded, and this is indicating only one hydrogen. So quadrate means neighboring hydrogen 3, and it means this is something like CH attached to the CH3. Okay, if you see this information here and this one are common, right? Now from these signals 2 and 4, we can clearly say that this compound contains this moiety, and probably this carbon attached to electron withdrawing group. And what it could be? It could be nitro. That's why it is going in the highly de-shielded region. Okay, this is 4 signal is quite de-shielded region. Okay, so from the carbon NMR, we understand that the compound has ester group, 2 methyl carbon, 1 methane, and 1 CH2. And from 1H NMR, we understand that this has O, CH2, CH3. So this could be the part of the ester. So the ester is like this: O, CH2, CH3. And this part could be like this, something attached to the electron withdrawing group nitro. It could be nitro attached to the CH3. Okay, now let's combine these two and see what we will get. So to satisfy the valency of this carbon, we can put ester group to this NO2. This is CO, oxygen, CH2, CH3. So if this is the correct structure, then it must be consistent with the 1H NMR and 13C. So we have to cross check. So let's do it. Okay, so this methyl will show you doublet because of this CH proton, and since it is close to the nitro, so it can come around 1.5 ppm. Okay, so this is giving the signal 2. Okay, and this CH will show you quadrate, and since nitro group is attached, therefore it will go beyond 5 ppm. So around 5 ppm or somewhere around 5.2 ppm. This is quadrate, and this is the giving the signal 4. Okay, we have assigned signal 4 also. Now this one is giving signal 3, which is also quadrate, and it is quadrate because of this methyl group, and it is attached to the oxygen. That's why it is coming around somewhere around 4.2 ppm, right? And this one will give signal 1. Okay, so we have assigned all the signals to the proton NMR. So this is fully consistent with the 1H NMR data. Now we have to check carbon NMR. So this methyl will give signal around 16 ppm or 14 ppm. So there are two methyl. Okay, this is attached to CH2 then oxygen, and this one is attached to CH and then nitro group. So one of them will be 16 and one of them will be 14 ppm. If you ask me, because of the nitro group, which is strong electron withdrawing group, this belongs to the 16 ppm, not 14, and this belongs to the 14 ppm. And this CH2, since attached directly to the oxygen, so it is showing at 63 ppm, and this one attached to nitro and the carbonyl group, that's why it is going 83 ppm. And in the DEPT NMR, it was showing the positive phase. You remember, it was in the positive phase, and this carbonyl group will show 165 ppm, 165 ppm. So we have assigned all the carbon signals as well. So the proposed structure is fully consistent with the 1H NMR, 13C NMR data, and index of hydrogen deficiency, and hence this is the correct structure for the given problem. I hope you really like this NMR problem, and you must have understood that the knowledge of chemical shift value play a very crucial role in determining the structure of the organic compound.
So that's all for today. I hope this video helped To strengthen your NMR skills, keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.